The topic of these lectures, the short name is the S-matrix Bootstrap. And a slightly longer name would be this slow and unidimensional S-matrix Bootstrap, where slow stands for non-relativistic, so non-relativistic physics, and one-dimensional stands for really one-dimensional, where we just have a line. Now, before explaining this title a little bit better, let me just remind you that the way physics normally works is we start with some theory that we say this is the theory I'm working on. And then we want to compute something with that theory or that model. So what do? We do some approximation. We never know how to solve things exactly. We do some approximation, we get the result, and then we improve. We improve the approximation, get the result, improve, and that's how it works, right? So theory, approximation, result, and keep improving. Now, another way you could imagine thinking about computing a physical quantity, and what would be a physical quantity? It could be something like the distribution of galaxies that Ricardo was studying, or the magnetization of some material. You are computing some physical quantity that often, normally, depends on parameters. For example, if the physical quantity is the scattering amplitude, the outcome of a scattering experiment, it will depend on the scattering energies, on the scattering angles. It will depend even on parameters of your theory. And then you could ask, instead of trying to start with a theory, do an approximation, get the result, and improve, you could just go directly to the final result and say, what properties must this scattering outcome obey? It must obey unitarity, it must obey relativistic invariance, it must obey, you make a list of properties that you require, and you try, just based on those properties, on those symmetries, etc., you try to constrain, you try to fix, sometimes even, the object you want to study without knowing the theory you are studying. So it will be a little bit like a meta approach, where instead of having one theory, you try to study the space of possible outcomes. Now, what could this be useful for? It could be useful, for example, when you don't know the theory. For example, we don't know what is the correct theory of quantum gravity. We know at low energy that we have gravity, but at high energy we are not sure. It might be string theory, it might be something else. So a good example would be, suppose I want to study the scattering amplitude, which is this S-matrix object, when I send two gravitons against each other, so I have some collision, and I send two gravitons, and I get the amplitude for getting two gravitons in the future. I don't know what this object is, quantum mechanically. Classically, I do. It's about studying these propagating degrees of freedom that Ricardo mentioned. Quantum mechanically, we don't know. And we might ask, what's the space of such theories? Again, at low energy, we know that if the moment of these gravitons is very small, which is equivalent to scattering them at very long distances, we have general relativity. And then we start getting corrections to the theory that are telling us what's the fundamental theory of quantum gravity. And you could ask, what's the space of these possible corrections? And you could ask, what is the possible space of these amplitudes? It doesn't need to be gravitons. It can be something more mundane, like pions, or theory, or particles, where this scattering amplitude is governed by some strong force, for example. And then again, our methods for computation, our approximations, are often not that good, and so resorting to some kind of bootstrap-like approach could be very useful. Now, these questions of studying problems related to quantum chromodynamics or to quantum gravity in 4 dimensions and so on are very hard. They require using relativity plus quantum field theory, combining both, and trying to explore the space of possible theories. And so in these lectures, we are going to work with a toy model of this type of questions, which, as I said, is a toy model where space is one-dimensional. So there is space, and there is time, and that's it. Things are non-relativistic, so there's no speed of light. Everything moves at slow speeds. And we have particles that scatter, that come in with some momentum k1, and the other one with momentum k2. And we are going to study the amplitude for this process of these particles here that have some mass m. And there's only one type of particle, say. And here in the future, we have the particles with the same mass m. So these particles, they have the same mass m in the future. And now, if we have conservation of momentum and energy, what is the final set of momentum and energy of the particles here? Well, clearly, if this is K1, what's the momentum of this line? If I have conservation of energy and momentum. K1, right? Because there's no, and this one is K2. And so these elastic processes in 2 dimensions are quite simple. You just scatter with some K1 velocity, with some K2 velocity, and the final velocities are preserved. So this is by momentum and energy conservation. And there is some amplitude of probability for this process to happen, and this object here that I'm going to define now is what is called the S matrix. And the S matrix is the final result. It will be a function of what? A priori, it could be a function of momentum K1 and K2, right? But it cannot be a function of K1 and K2 because we have, well, it's not relativistic, so we don't have relativistic invariance, but we have Galilean invariance, right? So we can shift, we can go to the center of mass, we can change referential, we can change frame. So it should actually only depend not on the velocity K1 or on the velocity K2, but on the difference of velocities, K1 minus K2. And this S matrix, this function that depends on a single variable, K1 minus K2, that henceforth we'll call K. This function of K is the S matrix. We'll define it carefully. And this is the final result. We could say, I don't care about what theory, what are the details, what is the interaction between these particles. I just care about this S matrix. And then we could try to study the space of this S matrix. We could ask, it's an infinite dimensional space, right? Because it's a function. And this would be, here, inside this space would be the allowed space of S matrices. Some good S matrices would be inside this. And here, this would be the space of forbidden S matrices S of K. Right? And what are the X's? It could be ways of parameterizing this function. It could be the value of the function at some particular momentum, for example. Right? We have an infinite dimensional space because it's functions, so functions are. And we parameterize it somehow, and we have something is allowed and something is forbidden. And so this would be the bootstrap. And the reductionist point of view, the microscopic point of view, of what we are studying is just Schrödinger equation. Right? So we are studying Schrödinger equation in 1 dimension. It's non-relativistic. We have some potential between the particles. We have Schrödinger equation. Each potential gives us a different S matrix. Or I forget about these microscopic details and I try directly to go for the space of S matrices. And that is the logic of the course. Now, if we want to jump directly to the space of possible S matrices and start asking questions about what's possible and what's impossible, we need to know very well what is this S matrix, what are its analytic properties, what must I expect, and for that we'll need to study many examples. And so we'll start first understanding what is the S matrix, studying examples of S matrices and trying to learn general lessons about S matrices. That will take us like 2 lectures. And then in the last 2 lectures, we will go and ask, now that we know what the object is, let's try to fix it, forgetting about these microscopic details of where exactly it comes from. Very good. So let's start with Schrödinger equation to set the ground microscopically. So we have an interaction between 2 particles, one at position x1, one at position x2. There is some potential, V, that will depend on the difference x1 minus x2. The combined state has some energy E, and so this acting on the wave function that depends on x1 and x2 equal to 0. So this will be our microscopic equation, our fundamental equation that will describe our wave function. And as I said, this equation is invariant under translations. If we shift all the x's, this is a symmetry. This is just Galilean invariance, right? Which means that we can write this wave function as exponential of I, some total momentum k, times x1 plus x2. This is the center of mass motion. This is the momentum of the center of mass motion. And then some wave function that only depends on the difference x1 minus x2. Let us assume that these particles are indistinguishable bosons. And so this wave function should be even. And in particular, because of that, psi prime of 0 equal to 0. It's something we're going to use later. Let's just say it's even. Of course, this follows. Now, if we do it, then we just plug this equation, and instead of having two variables, we will get our fundamental equation that I'm going to write once, where I'm going to just write it like this, plus the potential V of x plus, minus the energy that I'm going to parameterize as k squared psi of x equal to 0. Now this is capital K, this is small k, and this would be our fundamental equation that would describe the scattering, the interaction between the two particles. X is the distance between the two particles. What's the physical meaning of this small k? So capital K is the center of mass velocity. What is small k? Well, it's the energy, right? If I parameterize this like this, this would be the energy, right? The full energy, but okay, it's the energy. But what's the meaning of k itself? Not k squared, just k. It's the relative momentum of the particles, right? So this k1 here, for example, this k1 would be something, and I'm going to get factors of 2 wrong, like k plus small k, and this guy would be capital K minus small k. And there are factors of 2. I forgot to say that I wrote some notes that are on the website, so you can check, and there are many problems there. So one of them is precisely checking, writing carefully what is K1 and K2 in terms of this case, and there you will fix these factors of 2. Okay, and so this is our Schrödinger equation. So, and to be specific, what kind of potentials are we going to be studying? Well, we'll study 3 types of potentials. V of x, by the way, this is curly V, this is straight V, just because I absorbed some 2m's and h bars and so on, right? So from here to here, it's clear how to go. And it's clear that this k squared is just a parameterization of the energy as well. It's just the energy times some 2m's, etc. Okay. And so for V of x, we'll have 3 possibilities that we'll study. One is local potentials, like delta function. So this would be delta function, or derivatives of delta function, etc. So this is what we would say it's an ultra-local potential. The other possibility is a potential that is 0, except in some finite range. And then in some finite range, it can be whatever. And this range here is going to be 2a. So, yeah. And this would be, we would call this ultra-local. This we would call it finite range. The potential is 0 if, so here, V of x equal to 0 if x is bigger than a. And then, finally, C, we could have some potential which has infinite range, but let's say that here it's smaller than e to the minus absolute value of x over a, so that a is again some finite range. Right? So there is some a that sets the scale. So it decays, but it needs to decay exponentially fast, at least at infinity. And this, we would call it, I forgot. Okay, decaying exponentials. What's common to all of them is that at infinity, v of x going to infinity is going to be 0. All these examples that I wrote here are attractive potentials. They were negative. That's not crucial. You can just flip the pictures and get repulsive potentials. That's not important. Right? You just flip this upside down, now it's repulsive. So these three examples here, randomly, I chose them to be attractive, but they could be repulsive. But there is these regions here, again, and here, where the potential V goes to 0. And this means that when particles are very far away, they are asymptotically free. So particles are free here. When the distances are very big. And so the wave function there, the wave function psi, in that yellow region, psi of x, I can ignore the potential. If I ignore the potential, my particle is free. The solution is just second derivative of x equal to minus k squared. And so the wave function is just e to the ikx, right? Or e to the minus ikx. And so the wave function, we can write it as e to the minus ikx plus, and then e to the ikx. Either of these would work. By equal, I mean it's quantum mechanics, so proportional to. Of course, I can normalize if I want, but proportional to. And this, we say, let's say that here I'm writing it for x bigger than 0. This would be the incoming wave. This would be the outgoing wave. And a priori, there could be a relative coefficient, a number. And this number is what the S matrix is. Okay? Now, when is this equation true? This equation that, let's put a box on it, it's also another very important equation. This equation, again, is exact. It's true for x bigger than a for cases a and b. If we are in cases A and B, or B. Right? Because then the potential after A is 0, so there it's exactly 0. Or it's true when X is much bigger than A if we are in case C. So in case C, we need to go really far away. Right? At 3A, 4A, it's already more or less okay, but it's asymptotically true, but it's not exactly true at finite X. This equation is already exactly true if I have an exactly finite range, right? If I have finite range 5 nanometers at 1 meter or at 1 centimeter, it's already I already reached the asymptotic region. And so this is the definition of our object S of k. And this S of k, as I said, is what's called the S matrix. Very good. Any question here?
I have
Yes?
Well, you didn't symmetrize the wave function. So you said that.
Okay, very good. So here, I wrote this wave function. Great question. So the question is, I did not symmetrize the wave function. I wrote this wave function for x bigger than 0. Right? So I have my particle, and I said, this is the wave function on the right. What's the wave function on the left? Do I need to write it? No. It is just the wave function on the right. Right? So I just, so because the wave function is symmetric, I just need to study what happens on the right. What happens on the left is just the reflection of that by this property here. Right? So we'll always study positive x, because negative x we just get for free. Right? So there is no information. It's because they are indistinguishable. I can just say x is the separation between the particles, and by definition it's positive. And I get no new information by studying negative x. Any other question? Now, this is the definition of the S matrix. Let me point out that there is a fun equation we can write that follows from this equation. So this equation implies this relation that I'm going to write now, and we can check that S of k is equal to, once I can use this equation, it's equal to the following. It's equal to psi prime plus I k psi times e to the minus I k x divided by psi prime minus I k psi e to the plus I k x. So this equation just follows from the yellow box there. You can just check that if you use that expression and compute this quantity, this here with a plus sign extracts this sign. This here with a minus sign extracts this. And because we make the ratio, the proportionality doesn't matter, and we get precisely the S matrix. Okay? Now, from this equation, it follows the first few properties of our S matrix. I can now take that equation so that equation, we are going to use it later. But from this equation, you see that what happens, for example, if I plug minus k instead of k. Right? If you plug minus k instead of k, look, here it becomes a minus, here it becomes a plus, here it becomes a plus, here it becomes a minus. Right? Sorry? You invert it, right? So from this equation, the following property is obvious, which is that S of minus k equal to 1 over S of k. Another property that also follows is that S of k star, if I conjugate that equation, that this is equal. Well, if I conjugate the equation, I have to conjugate everything. It flips a few things. And you can check that you get S of minus k star. Okay? And so these two properties for the S matrix are going to be important. What you can already see from here is that because of these properties, in fact, when you will have the S matrix, and we will at some point study the S matrix as a function of k in the complex plane. And if you think that you have the complex plane, all the information is here. Right? All the information is already here, including the x's. So if I know the value of the S matrix in this region, then you see that from this equation here, I go from k to minus k conjugate, that tells me that here and here things are related. If this is k, this is minus k conjugate. And if this is k, this is minus k, and then I can reflect again to go there. And so this S matrix, if we knew it for here in this quadrant, this would be enough to get the full complex function S of k. Somehow all the information is there. It doesn't mean it's easy to study it just here. Sometimes it might be better to just study it in the full plane. But if we knew the function here, we would then be able to just use these symmetries to know it anywhere else. Okay, very good. So again, we have two particles. We go to the center of mass. We get a single equation for the relative separation between the particles. K is the velocity that they are approaching. Asymptotically, this describes the solution is an incoming wave and an outgoing wave, and the relative coefficient is called the S matrix, the scattering matrix. This S matrix is an object that we want in principle to study its space, so we need to know very well what this object is. What kind of functions could it be? For example, can I write any function I want? Of course, if you write a crazy function, it will already fail respecting these reality properties or these transformation properties. So already this tells you cannot write anything you want. You need to be something according to those properties over there. But we will have many more properties that we'll have to impose. And this S matrix can also be extracted from the wave function from this simple relation. This is going to be useful because later we are going to ask, could this S matrix blow up? Could it have poles? Well, maybe. Let's see if this factor could be 0. Could this S matrix have 0? Maybe. Let's see if this factor could be 0, and so on. So later we are going to start asking about the precise value of the S matrix in the complex plane. And there it's good to look for zeros here or zeros there to start studying this subject. Very good. Now, before moving on, I want to stress that this is a solution to Schrödinger equation, to the Schrödinger equation written like this. So given some wave function, how do you time evolve this wave function? What's the time evolution of this wave function? You just multiply the wave function by e to the minus energy times time. Right? So it's just a boring phase. So you get the wave function and the time evolution, you just multiply by a phase, and the wave function is the same, just multiplied by a phase. And so you could ask, why do you call this a scattering thing? I don't see anything scattering. I just see a stationary state and a phase that rotates the stationary phase. Why do we call this why do we say this is an incoming wave and this is an outgoing and things scatter? What is scattering? I just have a stationary state that is rotating with a phase. So, and many of you probably know the answer to this, but I wanted to clarify those that have this confusion or that now have this confusion. Yes?
Yeah, when we talk about scattering, well, this solution is only valid for x greater than a.
This solution is valid for x greater than a, yes.
Yeah, but so our S matrix is only value outside for long a's, but the interaction should happen for small x close to 0. So.
That's right. So the S matrix is the final outcome. So the interaction is like a black box. I don't know what happens. So I'm an experimentalist. I send particles and I receive particles and I measure the S matrix.
Okay, so
that's what we do. What happens inside depends. Depends on the interaction. If it's a delta function, if it's a well, it depends on the details, of course. So different potentials give me different S matrices. That's clear, right?
So we're just studying the outcome of an interaction.
Right. So this is our physical observable. It's the scattering outcome. It's like at CERN. You study the scattering of particles, right? But what do you see? You see tracks of particles going out. You don't go inside and ask what happened. I mean, that's what the role of people that do computations. We do the computations, we sum all the Feynman diagrams and so on to predict the final outcome. And then an experimentalist measures the final outcome. And the analog of those tracks that we measure at CERN and so on, in this toy example, is just this function S of k. Right? So this would be the analog of that. Please keep the questions coming. Okay, very good. So let's first understand this simple thing. Why do we call this S matrix something related to scattering? And why do we call these two waves an incoming and an outgoing wave? And for that, let me first, so now let's discuss S of K and scattering. And first, let's remember that particles, this e to the I kx, this wave function, if I tell you I have a wave function that is e to the I kx, what would that mean? That would mean that the absolute value of the wave function is just 1, independent of the location, right? That's not what a particle is. A particle doesn't have equal probability of being found everywhere. Because a particle is not just a plane wave. What's a better approximation? What should I do to try to mimic something better that would be a particle? A wave packet, right? A particle is something, it doesn't have definite momentum. It also doesn't have definite position. It has a little bit of both. It tries to have definite momentum and definite position. It's a wave packet. So let's prepare a wave packet. Let's say that we take this wave function. This is the solution. But this has definite momentum k. But in the real world, you don't have definite momentum. You have a linear superposition of momentum. And so the more precise wave function that we would get experimentally would be something where you would integrate with a wave packet. It can be a Gaussian wave packet, but that's irrelevant. K minus P. So let's integrate this in K. Right? Alpha is some parameter. We are saying the momentum is approximately equal to P. Okay? And then, what do we have? We have that wave function. Let's add the time evolution. Let's consider really the honest, let's write that wave function. So this times that wave function there, which is e to the minus I kx. But now let's add the time evolution. The time evolution is minus I k squared times time. Okay? And then there would be plus S of k e to the I kx and the same time evolution. It's just minus I k squared times time. Okay. And now let's focus, let's ask, this is our wave function. Let me use capital psi to distinguish from that usual psi. So this would be our wave packet wave function. And we ask that with time evolution included, so it would be a function of x and time. And we ask, where is this wave function localized? Where is it? Well, you see that if the momentum, where is this localized, this integral? If k that you are integrating is far away from p, this is 0. Because we have a Gaussian, so the momentum needs to be around p. Otherwise, the Gaussian kills it. But that's not enough. If x and t are both very big, this oscillates like crazy. Right? So even if k is close to p, if x and t are huge, this oscillates like crazy, it kills the integral. Right? You just have some crazy oscillations. So we need not only to be at k equal to p, but we need to be at a location where the phase is not changing much. We need to be at a stationary phase. Right? We need to be at a value where the derivative of the phase is 0. Otherwise, the integral is killed either by the Gaussian or by the oscillations. And so if we look at the value where the phase is not changing, what we get, so the saddle point, or the value where the phase is stationary, it's the same. The stationary point is taken by taking derivative, so I get minus I x, I take derivative with respect to k, minus I x, minus I 2p times t equal to 0. So I took derivative and I evaluated at k equal to p. And so I conclude that this term here, the first one here, so this is for the first term. In other words, the first term only dominates when x is equal to minus 2p times t. Okay? So that's when this term matters. Right? Now, let's say p is positive. So just to set some convention. X, remember, was positive, because we said we only study x positive, the rest is trivial. So can I obey this equation for time negative and positive? No, right? If p is positive and x is positive, t needs to be negative. So we see that this term only contributes at negative t. That's why you call it incoming. It's a term that matters when t is negative. Okay? So the first term, so we conclude that the first term, this wave packet, we have this wave packet, and this wave packet is localized here, and this is where the first term matters. Right? And this is nothing but the trajectory of a particle with velocity p. Right? There could be some factors of 2. Normally it's k squared over 2, and then the velocity would be really p. Here there is 2p because it's v1 minus v2. Okay? And then here, after, at positive times, the first term is exponentially small. It just oscillates like crazy, and there's no way I can make this phase 0. Let's now analyze the second term. When does the second term matter? Well, the second term, so this is for the first term. Now for the second term is very similar, but with a different sign that's going to make all the difference, of course. So for the second term, we get a similar equation, x equal to plus 2p times t, right? Actually, if we are more careful, and let's be more careful, if I put this x in the exponent and I also vary with respect to s, I would get minus, okay, let me write and then we try to fix, 1 over I dp of logarithm of s of p. So, okay, this is probably correct. And so what do we see? We see that now, let's first ignore this term and think that x and t are very big. If they are very big, they are bigger than this term, so it's what matters. When x and t are very big, again, we see that this equation only works for t positive because p is positive. And so we see that now we get the particles scattered here. But there is a shift by this term that says that particles don't arrive at my detector as they would if they don't interact. If they don't interact, remember there is another particle on this side, but we just studied the right part. So this would be what happens if they would just pass by without interacting. But because of the S matrix, there is a shift. Let's draw this shift. If I put t equal to 0, instead of getting x intersecting at 0, x intersects a bit to the left. Right? So I can say that this would be to the left. So this, so there is an explosion here. Here I don't know what happens. And then this delay, this would be a space delay, which is 1 over I ddp of log of the S matrix. So this would be another way of detecting this S matrix. If I'm an experimentalist, I do an experiment, I send particles, I know they would arrive here, and if they arrive a little bit to the left, the distance is the derivative of the S matrix. Okay? So now we see that not only this is indeed, it makes sense to call this in, it makes sense to call this out, and we also understood that S as an interpretation as being directly measured as a time delay or a space delay or space advance. So the sign of this quantity being positive or negative would mean if the particle arrives at the target before or after it would if the particles were not interacting. Right? I was a bit confused when preparing these lectures, and I realized I learned something obvious, which is you could think that you could guess easily the sign of this. And it's not true, actually. If you think a little bit harder, it's not so obvious what sign it should take. You could think if it's attractive, the potential is attractive, the particle would come, it would spend a long time because it's attractive, right? And then it would go out, and then this delay should be positive. But on the other hand, you could say no, because if it's attractive, it speeds up. And because it speeds up, it gets faster and bounces back. And indeed, you can have attractive potentials depending more precisely on the shape of the potential. You can sometimes get there earlier or later, and the delay, it's not just about being attractive or repulsive that you can fix the sign directly of this. Okay? So for example, for a delta function with an attractive potential, we speed up. And with a repulsive potential, we slow down. So it's not so obvious what the sign is, but this is the physical meaning. So that's what happens. So when we have a stationary state, of course, we just have a stationary state. The evolution is just a trivial phase, and nothing is, strictly speaking, evolving in time because we have the state and it's stationary. But physically, that's not what you do. When you get a stationary state, you convolute it to the wave packet, and immediately then you see that one of the terms dominates in the past, one dominates in the future, and the relative coefficient between the two is the S matrix. And this should mean that if this is true, notice also something, that here you come with a wave function that was coming in with amplitude 1, right? And here you get a particle that goes out with amplitude S of k, right? But probability should be conserved, right? Do you agree? Probability should be conserved. The particle comes in, particle goes out. So you should guess that this guy should obey that the absolute value of S should be equal to 1 for some physical particle with real momentum. Right? That better be the case, because otherwise I would start with a plane wave with coefficient 1 and get a plane wave with coefficient 3. And then it's like, what happened? How could probability work? Right? Okay. And this equation, it's our intuition that says this should come from conservation of probability. One of the problems of the notes is to show that conservation of probability implies this equation. And another problem of the notes is to show that that box implies this equation. But that one is more trivial. Let's do it right here, just by head. So if I have S, if k is real, then the star here is doing nothing. The star here does nothing. I can use this equation here, and I get 1 over S. I put S here, and I get S of k star times S of k equal to 1. Okay, so it works. So indeed, it was a nice box to have there. It immediately gave us, indeed, this expected equation. Okay? So when k is real, and when I do a physical experiment sending particles with some velocity, the absolute value of k should be 1. Okay. Very good. So again, S is the amplitude for this process. The absolute value is 1 for k physical. But the phase is not 1 and is not 0, it's non-trivial. And the phase, the argument of S, is very non-trivial, and it has directly a meaning as the delay when you have this scattering experiment. Okay? So phase 1 and argument, absolute value 1, and the argument is related to the time delay. Very good. So this is what we learned so far. So let's put here, in particular, let's write here that for real k, absolute value of S of k equal to 1 is a lemma, an important lemma that follows from this. And that physically, as we said, represents conservation of probability, the fact that the wave comes and the wave goes. Now, you could ask, what would happen if I scatter the particles and the particles come in and there are many possible outcomes? And the one we are studying is just one process, right? So suppose I have particles of mass m, they bash and poof, and they produce two particles, but other things could happen in the future. There could be other possible outcomes, right? Then, what would we say? We would say the amplitude is 1, and what would we say for the final amplitude of this process? Well, it needs to be smaller or equal than 1, because there are other stuff that can happen, right? So here we said it's exactly equal to 1, because we said that's the only process that can happen. We only have one particle, we are non-relativistic, there's nothing else, so two particles go in, two particles go out. But imagine this particle had a flavor, and it was a red particle, and there is a red and a blue particle, right? And I can have red-red, they can produce red-red, or red-blue, or blue-blue, right? And I can have many final processes. Then this amplitude needs to be smaller or equal than 1. Okay? So more generally, in more complicated situations, we have that absolute value of S of k is smaller or equal than 1. It's also true. I mean, this equation is also, this is true, this is also true. Right? This is more agnostic. It's just say, I have some process, it needs to be smaller or equal than 1. Maybe it's 1 if there's only one type of particle, but if there are more possible outcomes, it's smaller or equal than 1. Okay? So this would be the consequence of unitarity, of conservation of probability. This is what we would get if there exists more possible outcomes. And this is also true, because the equality is true, so the smaller or equal is true. Okay? And so that's an equation that's important to know.
Am I allowed to?
Sure, yeah, please.
So how do you say the yellow box if S is smaller than 1? Because from the yellow box you get S exactly equal to 1. For K real, no, you just derived earlier that S exactly modulus 1.
Right.
You allow the yellow box, but then if S is smaller than 1,
If S is smaller than 1,
you have to tweak something here.
right. Okay. Good question. I think I would have to tweak. Okay, that's a good question. Let me think about it. But let me say something. What would go wrong if I have more outcomes is that then my wave function with more outcomes is not this. The wave function is this plus the other outcomes, if there are other outcomes. And because of that, it's no longer true that I have this box. And because it's no longer true that I have this box, I have to be careful that that box is no longer guaranteed. So when I ignore this, I have this box, and then this box implies that. If I have extra terms, I have to be more careful, asking what of those properties I can derive without using this box. And one of them should be still true. Maybe, yeah, one of them should be true, and the other one I should need the box to derive, and that's what goes wrong in that case. We are not going to study that case, but I wanted to point that out. Good. So let's, so this is our S matrix. Let's compute it for some example. and start looking at its properties and see that it does obey the properties we are anticipating. And so let's start with the first example. It's the most important example, and it's the potential, which is this ultralocal potential, just some delta function. Okay, so I have some local interaction. The potential would be just like this if mu is positive, or like this if mu is negative. How would we solve this Schrödinger equation for the delta function potential? Who solved it in quantum mechanics? Delta function, just Schrödinger equation that I wrote that was here in some box at some point with delta function potential. Sorry? Fourier transformation is not a good, well, strictly speaking, Fourier transformation is usually not a possibility because the potential breaks translation invariance. I'm not sure what exactly you mean by Fourier transformation. If you yeah.
You can take 0, then you use continuity.
Okay, so those are all true. So, but again, as we said, when would this be true in that case? This equation, when would this equation be valid for the delta function? Everywhere, right? Because the potential is ultralocal, so everywhere except at 0. And so all we would have to ask is, we have that equation, this equation is true, and we have to make sure that 0 is okay, right? And for 0, let me just remind you how it works. The way it works is that you have minus psi prime prime plus the potential, let me write plus mu delta of x psi plus k squared psi equal to 0. And psi, you know, is given by this equation here. And so what you can do is just integrate this equation from minus epsilon to epsilon. And then the integral of this equation from minus epsilon to epsilon, from here, it gives you minus psi prime at epsilon plus psi prime at minus epsilon. It's a derivative. Here, it's a delta function, so it just gives plus mu times psi of 0. And this is very small. It gives me order epsilon. And so all we conclude is that the derivative, right, this is equal. This is even, so this is equal to the derivative to minus the derivative at epsilon. And so I conclude that I can fix that psi prime at 0, when I send epsilon to 0, must be equal to mu over 2 times psi of 0. And so basically with this property, if you know that this is the S matrix, and if you compute that quantity there and you impose that this equation is true, it fixes the S matrix. Right? You just take derivative at 0 of this, you compute function of 0 of this, and you plug it there and you get the S matrix. So if you do it, you get that the S matrix S of k is equal to k, and here k, and here there is plus I mu minus I mu, and I need to fix the signs and potential factors of 2. Yeah, factor of 2 and factor of 2. And so this is a very important S matrix, and this is the S matrix that we are getting for this potential. Okay, so let's look at it and let's see. First of all, let's look at these properties and check that it does obey these properties. So putting k to minus k, indeed, just flips it, right? You can see it right away. Conjugating this equation, if you conjugate, you flip the sign here, you flip the sign here, and you put k star, k star. So if you conjugate, that equation is precisely true. If I put minus k star, it's also true. Is it a phase when k is real? Yes, when k is real, I get that it's a ratio of something over its complex conjugate, so it's a phase. Right? And finally, if I wanted, I could compute, as I said, the time delay, d dk, 1 over I of logarithm of the S matrix. And if we did it, you would get something like mu over k squared plus mu squared. Perhaps over 4, yeah. Over 4. Okay? And so this would be this time delay when particles come in, particles get out. And this would be its delay. And for example, notice, if k is huge, the delay goes to 0. That's obvious, right? If the particles have huge energy, they don't see the potential. If mu is very small, it goes to 0. If mu is huge, it also goes to 0. Why? Because if mu is huge, it's just a wall. Particles, boom, just bounce, and that's it. Right? So it has all the nice limits you could imagine. And this would be the time delay for this particular S matrix. So let's look at this S matrix. And so we checked what we knew, but let's try to see what this is telling us and ask if this is general or not. Okay. So let's try to, from this example, this is the definition of the S matrix, like we said. It implies this equation that we are not going to use today. I can erase, we are going to use tomorrow. And let's try to see what properties this S matrix, what other things this S matrix has. So first of all, we see that S as a pole at k equal to minus I mu over 2. Okay? So it has a pole. So the first question is this a physical thing? Is there a physical meaning to a pole of the S matrix? Okay? That's a question, right? So what does this mean? What is it? The second property that we see from this S matrix is that S of k goes to 1 as k goes to infinity. Right? When k is very big, S of k goes to 1. And let me emphasize that here I mean anywhere in the complex plane. Right? Not for real k, but for any k, right? I can take k to go to infinity in the imaginary direction. And if this is the k space, we are saying that as I go to infinity here, the S matrix goes to 1. And if I go to infinity here, the S matrix goes to 1. If I go to infinity here, the S matrix goes to 1. Now, this property that when you approach infinity, things go to 1, doesn't matter what direction you approach. Mathematically, you can say it means that 1 is not an essential singularity. An essential singularity is the opposite of this. A point is an essential singularity when you approach it through different directions, you get different results. So here it doesn't. So here, we see in this example, we see that infinity is regular. And that means there is no essential singularity. And we also see the S matrix as a pole. And now we could ask, are these properties general? Do all S matrices have poles? Do all S matrices have regular behavior at infinity? And the answer is no to both. Poles will have a very special physical meaning that we are going to analyze now, and we'll see when do we have poles and when don't we have poles. And this fact that it's regular, it is not a general property of S matrix, it's a general property of S matrices for type A. If you have an ultralocal S matrix, you don't have an essential singularity at infinity. If you have a finite range potential, you have an essential singularity at infinity. So it's not that you might have, you do have. And so it's not about being picky, you have to be careful. Okay? And so we will now understand that this, what we will see in these lectures is that this is true for potentials, for A-type potentials. And we will see that these poles of S matrix physically correspond to bound states. Like in the hydrogen atom, it's a bound state of a proton and an electron. Right? And so they have a very clear physical meaning, these poles that we are going to discuss now. And this behavior at infinity, in the complex plane, it's something we have to be careful, because if the potential is not ultralocal, you might and you will get essential singularities. There was a question? Yes?
The function going to 1 and not to 0 means that it's not analytical, right?
The function going to 1?
At infinity. Because all analytical function on the complex plane should go to 0.
Why?
Isn't that a theorem?
No.
Because
1, the constant 1 is as analytic as you could get, right? Function f of x equal 1. I mean, no one is going to say it's not analytic. Or it doesn't decay at infinity.
yeah.
Fine. Why would it decay, right?
Fair.
Okay. Yeah. Sure, yeah. When k is going to 0, the S matrix is becoming effectively -1. And that's the... So at very small momentum is as if the potential is huge compared to that momentum, and therefore the wave function needs to be 0 there. Well, the derivative would be something, but it's the derivative. When you mean here, when k is equal to 0, I get some value that is constant, and its magnitude depends on mu. So when mu is finite, I just have a very slow wave, and then it gets out very slow again, but with a shift, which is given by this. When k is very small, if k is much smaller than mu, the shift is proportional to 1 over mu. It's probably the only dimensionful thing you could construct. Okay. So the question is, what's the physical meaning of these poles? And the message, as I already anticipated here, is that these poles are related to bound states. But let me be a bit more specific. The slogan that you should have in mind, or the main statement, is that bound states, if you have a bound state, so bound states, they lead to poles. Poles, you need to be more carefully, they don't necessarily lead to bound states. You have to be more careful, and you have to analyze it a little bit more carefully. An example is this potential. If the potential was this, exponential of minus x over a, you would have many poles in the complex plane. Some are bound states, some are spurious poles. So if you have a bound state, you have a pole, but if you have a pole, you have to be careful, it might not be a bound state. let me be even more specific. Poles, bound states are poles. This is true always. Poles are bound states for cases A and B. Poles don't necessarily mean bound states for case C. That's a more precise statement. So if the potential is finite range really, or local, then it's okay, it's safe. Poles and bound states are going to be exactly the same. But if the potential is decaying, but it's not strictly zero, then you can have spurious poles that might not be bound states. And so the implications are like this. Okay, but the most important one by far is to understand this box here, which is the standard scenario, the generic case. And let me remind you why poles of an S matrix correspond to bound states. And the reason is in that box where we wrote the asymptotic wave function. So here is the wave function. And so now if you have this wave function, you could ask, K is real, right? It's the energy of the scattering experiment. Could K be complex? What would go wrong if K is complex? Why would you normally discard K complex in this equation? What would go wrong with this wave function if K was complex? It would explode, right? If K is complex, who would explode, this or that? Sorry? X is positive. Who says the first one? Who says the second one? First one. Second one. Good. It depends on the sign of the imaginary part of K. Right? So if the imaginary part of K is, okay, so typically, so generically, so let's say K complex, generically leads to psi of x going to infinity. And we can see that if the imaginary part of K is bigger than 0, e to the minus I kx goes to infinity. And if it's smaller than 0, e to the plus I kx goes to infinity. Is this true? Let's say. If K is IA, yeah, it's correct, right? It's correct. Do you agree? K is IA with A positive. I put here IA minus, I get plus. Indeed, it explodes. So it's correct, right? X is positive, right? And so if the imaginary part of K is positive, the first term kills me. If imaginary part of K is negative, the second term kills me. Right? So what would you like to do? You would like to be able to drop the term that kills you. If you could drop it, it would be fine. So let's suppose imaginary part of K is positive. If the imaginary part of K is positive, this term is bad. Right? This term is the one that explodes. How can you keep only this term? You can keep only this term if K explodes. If K explodes, then you just take this exponential if you are at the pole. Do you agree? Another way of seeing it is divide the full wave function by S. Then this has coefficient 1 and this has coefficient 1 over S. So if 1 over S goes to 0, I can kill that term. Right? Again, remember the wave function is projective. All that matters is the relative weight of the terms. And so I want this term to be much bigger than this so that I can keep only this term. Then it would decay at infinity. And that would be the definition of a bound state, is something that decays exponentially at infinity. So generically, it's a problem, but the exception, and a very important one, is unless K is located at the pole of S. If we are at the pole of S, then my wave function is proportional to e to the I kx. And this goes to 0 if the imaginary part of k is bigger than 0. Right? So what do we conclude? We conclude that we can have poles, we can form bound states if we go to a pole in the upper half plane. In the upper half plane, a pole is a bound state. Not in the lower half plane. Because in the lower half plane, if I go close to a pole, I also drop the first term, but then this explodes instead of going to 0. So not in the lower half plane. So the claim is that bound states lead to poles in the upper half plane. And so the picture that we have is that in the k-plane, we can have poles here, and these poles would correspond to bound states, where when I'm at the pole, if this is k at the location k equal to I kappa, let's suppose it's purely imaginary, then at the location of this pole, my wave function is e to the minus kappa times x. And that's the definition of a bound state. It's a wave function that decays exponentially far away. And now let's look, where was this pole? This pole was at k equal minus I mu. Is it in the upper or lower half plane? Depends. Depends on mu. When is it in the lower half plane? When mu is positive. And in the upper half plane, when mu is negative. Does it make sense? Physically? Yes. When mu is negative, the potential is attractive, right? It's an attractive potential for negative mu. And for negative mu, we have this potential that supports bound states. Right? If mu is positive, the potential is upside down, it's repulsive, and there's no bound state. And that's exactly what we see. We get the pole, but the pole is in the upper half plane only when mu is negative, when the potential is attractive. So I also wrote these poles here in the upper half plane. Not only I put them in the upper half plane, I decided to put them exactly purely imaginary. Right? This we did not prove yet, but we are going to prove it next time. That not only they are in the upper half plane, but they need to be purely imaginary. Okay? That's kind of obvious that physically that to be the case, because if you remember, when you have k in the complex plane, the momentum of the fundamental particles was center of mass plus minus k. Right? And so what you want is the total momentum to be real, and the fundamental momentum could be complex, but you don't want to start having... No, okay, no, I take it back. No, that's not a... Sorry, I take this back, this last sentence. No, that's not a good argument. We will see tomorrow why not only they need to be in the upper half plane, that we saw now, but why they need to be precisely along the imaginary axis. So... yeah, very good. And we are right on time, so I think now we have the time for questions. Yeah. Yeah.
What is the physical meaning of k being purely imaginary? Is like virtual particles?
Is what? Sorry.
Virtual particles.
No, it's not virtual particles. So there's nothing. It's not virtual particles. It's just that my wave function is just given by this in this case. Right? It's a physical particle. The particles are physical. They just like to be close to each other. Right? So this tells me that my particles, if you remember, what was the total wave function? The total wave function, if we go back, was e to the I k, capital K, times x1 plus x2. This tells me that they move. But now we see times e to the minus kappa times absolute value of x1 minus x2. So you have the center of mass is just moving, the two particles, but they like to be close to each other. Right? The interpretation of this is that this k have some complex part, and they form a bound state. So the composite, the two particles, you can think that they have complex momentum, but the total momentum is real. The total momentum is capital K. And the total energy as well. So if we compute the total energy, it's K plus I kappa squared plus K minus I kappa squared, which is 2 kappa squared minus 2 curly kappa squared. Right? And so what we see is that the energy of the state which has these two particles is real. You see that it's smaller than if you just had two particles, each with half the momentum. It's smaller by this amount, and so that's indeed a bound state. So if you have two particles, say each with momentum k/2, and that's it, versus when they form a bound state and the energy is lower.
That's like an elastic collision.
That's what a bound state is. It's when you form, where the two states have some binding energy, and therefore the total energy is less than the energy of the particles. And now they don't get far away from each other. Uh-huh.
If we consider relativity, how would we consider that Lorentz transformations can change time ordering in events if there is some space separation?
That's a great question. So let me rephrase the question a little bit and say, what would change if we have relativistic invariance, right? So what would happen if I have relativistic invariance? And one basic thing that happens is that when you have relativistic invariance, you can change time and space, right? And so this S matrix, we have been studying, there was past, there was future, but now when you have relativistic invariance, whenever you have this past and future, there's also left and right, which you can swap and so on. So this structure that is here for past and future is what we call a channel. But there's the other channel, which is left to right. And so there should be twice as many poles, twice as many axes, and so on. And indeed, I'm going to explain a little bit what happens when we go relativistic in the last lecture. And what we will see is that indeed the number of structures duplicates. But then when we take the non-relativistic limit, one set goes far away to infinity, and we are left with what we are seeing here. So the separation between the speed of light becoming effectively infinite decouples the relativistic effects. But there's more, things are a little bit more complicated when we do relativistic invariance. That's why I decided in the lectures to stay non-relativistic. Yeah. But I'll comment at the very end about what changes. Yeah.
So you talked about poles on the plane and essential singularities on infinity. How about essential singularities on the plane?
Essential singularities on the plane are forbidden. You cannot have. You could see from this equation where we wrote what's the definition of the S matrix as a ratio of these terms. And from there, you see that your wave function solves the differential equation, so it cannot develop essential singularities at finite k. Right? Your Schrodinger equation could not, just as some random finite k, develop an essential singularity, just because it's a differential equation. Right? And that's it. So just that. In other words, to generate differential equations, to generate essential singularities, it's not totally trivial. If you have like the equation that gives, if you have a differential equation, and then for finite values of parameters, there's no essential singularity. Essential singularity is something weird, right? It's a point that you approach in different directions, and you get different behaviors. It's not the norm. Yeah. Yes. So the question is, if you have many outcomes, do you have many S matrices for different outcomes? The answer is yes. Yes. And therefore, for example, the S matrix could become a real matrix, right? Because now you would have, what are the possible outcomes? You could have particle of mass, for example, m goes to m prime m, etc. All these possible processes. And so now the S matrix, you really should say, I want to study the amplitude for m goes into m prime, etc. So your S matrix is really becoming a matrix. There's really what is the initial state and what's the final state, what's the initial state, what's the final state, and depending on the states, I have a different function of the center of mass energy that I scatter at. And now the equations that were equations for a function become equations for tensors and for matrices, and I have to be more careful. For example, 1 over a function is easy, but if this is a matrix, what does 1 over a matrix mean? It's probably inverse of the matrix, right? It's true, it's inverse of the matrix. So sometimes it's easy, sometimes it's a little bit non-trivial. Yeah. Now, here we are doing, it's Euclidean, I mean, it's you can say it's Minkowski space, yes. But there's no Lorentz invariance. The transformations are Galilean invariants, right? It's a Galilean space. There's time and space, and there's no rotation between the two.
But I mean, for having a complex momentum, you need to extend the Euclidean plane to a Minkowski space?
No.
Or what do complex momentum means here?
So complex momentum, generic complex momenta, means nothing. I just have a function. So when we do an experiment, we will do it at real momentum, right? Positive, because otherwise the particles are moving away, they are not going to scatter. So we have to prepare the particles and send them against each other. So the momentum needs to be real and it needs to be positive. Then they collide. But as a function, this function, I could define it in the complex plane, and I could explore the full function in the complex plane. And generic values in the complex plane have no physical meaning, but specific values could have a physical meaning. For example, poles have a specific meaning. Poles give you the bound states of the theory. So that's an example of a very physical meaning of in the complex plane, right? Yeah.
If we're not doing the theory behind that, if we're measuring the collisions on an actual experiment, can we calculate the S matrix only from real data?
If you just do an experiment, and if you are just measuring S, what would you do? You would do the experiment at many momentum k, many times, because it's quantum mechanics, so you need to do it many times, and then you will get a function S of k for real k. If your function is holomorphic, which means it's a usual type of function of k, if you know the function in a segment, you can analytically continue it and get it everywhere. You would probably not care. If you did the experiment, it's done. I mean, you already have the result for physical things. So, but yes, theoretically, in principle, when k, so let me stress what was already common in 2 questions. When we do an experiment, we are here. This is the lab. Right? We are at a real momentum. Let's say positive. Then positive or negative are related by a trivial symmetry. But let's say here, this is where we are. Then this is also physical. It's bound states. And here we got 1 at infinity for ultra-local potentials. And we will see how to modify it tomorrow if it's not ultra-local.
Does that tell us something about the potential we're working on? Can we find something about the actual collision?
Great. So that's a very cute question, which is, we know that the microscopic model is Schrodinger equation. So given a potential, I compute the S matrix, right? That's the way it normally goes. But you could ask, could I, given an S matrix, can I reconstruct the potential if I really knew the S matrix completely? And this problem is solved, and it's true. If you know the S matrix, you can reconstruct the potential in one dimension. And one of the exam questions of one of the previous journey school is precisely about that. So if there is some fun equation that if you are given some S matrix and some location of the bound states, you can reconstruct what potential did it come from. But it's something normally we don't learn in undergraduate. Yeah. Maybe in Russia. Yeah. Yeah.
What's the fancy kappa?
No, fancy kappa was the location of the pole. I called the pole K, I called it I kappa.
Okay.
And that was just the location in the upper half plane.
And could you elaborate the limit where you are approaching the pole? Because I mean, I suppose that as you approach the pole, S of kappa increases, but how would you take the limit to the wave function goes to 0? Like.
So maybe it's easier if I write the wave function in an equivalent form. I divide by S of k here, right? And then here I put 1, right? Then I say I go to the pole. I go exactly to the pole. I don't approach. I go there. If you go to the pole, this is infinity, this is 0. And I kill this. And then I'm here at the pole, and that's it.
Okay.
Well, let me already anticipate. What you could be thinking is this equation could be an approximation, right? Because it was exact in these cases A and B. But it was an approximation in case C. Right? In case C, we said that this is only true far away. And then we could be careful that there could be ... that's some small corrections to this equation. And you could be afraid. Could it be that when I go to a pole, and I naively drop this and I keep only this, could those ... become important sometimes? And could that be an exception to the statement that poles here become bound states, etc.? And indeed, that's the case. So that will be related to that, but we will see it later, tomorrow, or whenever my next lecture is, we will see that exception. But for now, you can say I have this equation. It's true for cases A and B. Suppose we are in cases A and B. I go to the pole, 1 over infinity is 0, I drop this term, and I keep only this, and this is the exact wave function, it's just exponential.
Got it. No, thank you.
So there are 12 problems for today's lecture. So, but many of them we solved already as we went. So. But you can have a look, and for tomorrow there are 37 minus 12 problems, 25. So you can start solving some of tomorrow's as well. Yeah.
For processes where we have actually hard to create, or I mean, because it's like as if the probability, the S matrix, the modulus of the S matrix would be greater than 1 actually.
No, greater it can never be. Because greater, it would mean that I start with amplitude 1, yes, and I get amplitude 3. Okay. That cannot be. The probability will increase. Now, the probability can decrease if there are other outcomes, but it cannot increase.
Okay. Okay. But how do we describe a process where we have more particles coming out?
Then it's smaller than 1.
Oh, it's smaller than 1.
Smaller than 1. Because if you say the probability of getting the same type of particle is 0.7, it means that there are 30% of probability of getting other things. Okay. Right? So if your amplitude for your process of particle mm go to mm, if the amplitude is 70%, it means there are 30% chance of getting other possible outcomes in the future. So having possible outcomes manifests itself in the elastic component as the elastic component being smaller than 1. Right? Because if that probability is smaller than 1, it tells you there's other stuff that could happen. Can you pass the mic there? Yeah.
So related to that, why K real means that is only one outcome? Because when k is real, all the probability is just for one asymmetry.
No. Okay. For real, so for our lectures, and when k is real, S of k is equal to 1.
Yes, but that means that is.
For more complicated setups, S is smaller than 1, but also for real k. This is always for real k.
Okay.
No, real k just means I'm doing an experiment. It doesn't mean anything about other processes, right? K is the relative velocity, so it's real. It's a real positive number,
Okay.
right? So if I'm doing an experiment, k is real. Now for k real, this can be 1, or it can be smaller than 1. Notice that our S matrix, where was it? The one I wrote here, it was k plus I something over k. It was something like this, right? Note that this is absolute value equal to 1 when k is real. When k is not real, it does not. When k is not real, the absolute value of this function is not 1. Right? It's when k is real. Which makes sense. It's when you are doing a physical experiment. The amplitude is 1. Okay, I think if there are no more questions, we continue tomorrow, and we can go for lunch. Yes.
So first, let's say I take k to 0 first. And then I take mu to 0, right?
Yeah.
Usually I would say the
Okay,
factor gets smaller and smaller.